Okay, I think we can start. Hello, welcome to my presentation. There's not that much of you here. At some point I thought maybe we could go to a bar and just talk about performance and complain about the weather. Okay, but there's too many of you, so no. I like when my presentation somehow is connected to a theme of the whole conference or maybe some other presentations. It makes it part of some bigger whole. And I was very glad when Bur Satter at the keynote pointed out that the economics of the software development has changed compared now to some few decades ago. It was keynote, so probably you all have been there. He said that a few decades ago, when someone wanted to start a software project, what it took is to buy a few servers, buy some databases, licenses, then more server, more databases, more licenses. It amounted to hundreds of thousands of dollars of capital expenditure to start the project. And right now, what you need is just a laptop and an account on some cloud vendor where you can buy servers for cents per hour, right? But make no mistake, developing software, software products is still very expensive. It doesn't go to hardware vendors or Larry Ellison yachts. It goes to wetware instead of software and hardware. So it means us. And it's good, right? We like being paid a lot. It's just that the economies the changed economies of producing such products changes how this is done and how the people are used, how the companies that invest in us and buy us to make products, how they look on allocating of people. So in this presentation, I will show you this impact, a few words about how this transformed how we work and what kind of skill set is needed from developers in such circumstances. And then we will go on a road trip to find out actually if there are cases when we want to actually invest those people into doing performance optimization and what it takes for us, for developers, what skill set is needed and knowledge to actually do this performance optimizations in a way that brings the most value to customers or to companies we work for. A few words about me. I'm Tomasz. I work in Codewise. Right now I'm heading a small startup founded by Codewise. It's called turnimo.io. It's a service as a service for monitoring applications. When I worked at Codewise, I was a tech lead. Some organization called it engineering manager. And for the purpose of this presentation, I like to call myself failed tech lead. Why? Well, if you join a small startup company that grows and achieves success, then suddenly you have 100 people in the company, there are teams, and initial developers are natural fits for leading those teams, but are rarely ready. So I went on the internet to read about what actually engineering manager should do or shouldn't do, and I found this little article, how to fail as an engineering manager in 8 easy steps. So I started reading and I failed in the first steps, keep coding. So I kept coding. If you've seen the quality presentation by Chet Hasse, you know that I'm one of those managers who still think that can code. And I do it sometimes. Fortunately, I have skin in the game, which means I am on call together with my team, so maybe that makes this code not that terrible. When I was rehearsing for this presentation, I looked at my history of my projects, the products that I created, maintained, optimized, and my constatation was that I spent about half of my career optimizing allocations in Java. I should rethink my life choices, right? So this was very sad. Let's visualize it. Okay. And you see this lady doesn't want to optimize allocations anymore. She just wants to go to Bieszczady. This is a front page of a small conference called FUDs. And FUD is something that is, well, short-lived, overhyped thing that's actually empty and doesn't bring any benefit. It's short, in this case, for failed aspirations in database systems. Ignore the database part. It was just a mini conference at the database conference, but what this conference was about is failed aspirations. So imagine conference that actually is about failures. It's not about new technologies, it's not about selling you a new kind of software or taking your private data so they can send you job offers. It's about failed systems. And you can submit a paper or presentation there when you talk about a system you worked on that seemed like a good idea but turned terribly wrong. Some of things they discussed was like XML databases there. But there's a lot of other stuff, right? Corba, right? SOAP, I don't know, maybe using JSON to communicate microservices, like sending terabytes of ASCII characters to communicate robots. It makes sense, right? Maybe it will be, someone will tell you this at the next installment. Actually, let's make a call for papers for this conference. Who wants to say something about their failed projects? Thanks. 1, 2, 3. Okay, we almost have 1 day of conference. I will make a keynote because it's easy to laugh at other failed projects or other failed technologies, but it's harder to talk about my own. A short story from Codewise, my team. We had an internal client. It's a great thing. Internal client, a guy who knows the business, he's always right, who will come to you and say, okay, this part of software is great, you should develop this, and I know the market, so this will work, right? What can go wrong? He was right most of the time, but at some point he came to us and said, look, we develop all this analytical software for our clients, and our clients use it all day long. Maybe we should, instead of, we should make it simpler for them, just analyze it for them and show them the summary. So it was just before the AI craze. Right now we would call it cutting edge AI, machine learning stuff, and everyone will throw money at us. But it was before this. So we started this project. It was, in a way, agile, so there were iterations. We talked to our internal client. We showed him the results. He said, okay, that's it. And by the way, the feedback from clients, if you have good feedback, it's not feedback, right? It does not tell you what to improve, what to develop. If you have bad feedback, that's a good feedback because you can act on it. If you have no feedback, then this is bad feedback because the client just doesn't care about what you released. And we were working on this project. It was a lot of fun. We had terabytes of data to process per client. We had to learn a lot about kernel, about file systems, SSDs, how JVM works, how can you map like unlimited terabytes of data in JVM, although it usually won't allow you to do it. It was a lot of fun. And to make a long story short, in the end, we released the product. Client didn't understand it, didn't like it. No one bought it. No one paid for this. So that was something that was a lot of investment, right? Because the people is the most important and the most expensive thing, and also the cost of opportunity, of lost opportunity, because we could have been working on something better. This slide is from no Fluff Jobs. You probably know it. They have a booth here. From their blog 2 years ago, salaries were about 16,000, 17,000. That's tops. I think it's very old. Right now, developer salary, I mean the top salary probably is about 19, 20, 21. Whatever. There's a high-frequency trading company in US that was looking for a DBA to optimize their database. They were paying $500,000 per year for this one person. And so this is pretty expensive. Let's assume that all the costs from the employer is about $10,000 per month for such person. Think about this. If you have a team of 8 to 10 people and they work for 1 year, it's $1 million. You look at the teams you work in or around you. Did you think ever that the work you did in 1 year, did it bring your company $1 million or more? In that case, this would be a good return on investment, right? A lot of companies started to trying to optimize, right? That's why there are development centers in Kraków. But also in the startup, Silicon Valley, the startup places when there's a lot of startups, people started to describe techniques to optimize this kind of development to make sure that when we hire developers, we better than know what they should do to actually provide a return on investment. One of these books, it's nothing new. I just wanted to point out how they think, how to test new ideas in just few days. The sprint is not related to Scrum or Agile. The main idea here is that you have 5 days, and in 5 days we validate if your product idea makes sense. These guys who wrote the book are from Google Ventures, so it's a branch of Google that invests in startups, and obviously if they invest in startup, they want to help the startup to succeed. I believe Slack was one of the startups they invested in. So the idea is that on the first day, they look for the clients that will come on Friday, on the 5th day, to look at your product. So you start with probably no product or something or a problem that you want to solve. And on Friday, you know there will be clients knocking at your door to look what you propose as a solution. So you have 4 days to actually design something. 3 days is spent on talking to subject matter experts, thinking about the problem, coming up with the solution. And on 4th day, on first day, you get to implement it. You have 1 day out of 5 to actually do anything software related. And actually, these guys say, okay, if your product is a web page, just make a PowerPoint presentation. The clients will think they're clicking on a web page, and it will be just rigged demo. I remember this from my studies when there was an end of term and we had to give a project, finish a project, and it wasn't ready, so we just faked it. I thought this was wrong, but actually it was market research. So these are the ways that a lot of companies will try to validate products and make sure that when the developers start working, they will be working on something that is important. But you might say, okay, but it doesn't matter, it's not about quality, right? It doesn't say that you need to, you shouldn't do tests or you should write bad code. It's just that you can make this code work by stopping around things that are already lying around with minimal invention, minimal optimization. You just put up some product to verify that it works with clients. And if it will be probably slow, right? Because it will be bloated, you will put Spring, you will put a lot of other stuff there. Well, okay, just buy a bigger server. This is Amazon 2-year-old server, so probably soon it will be cheaper or there will be much bigger server, 128 CPUs, 4 terabytes of RAM, 4 terabytes of SSD. It costs about $20,000 a month. It's not cheap, but if you reserve it, you will get it for a price of about $10,000. So you can have one developer work or something, or you can add 128 cores to your product. It's similar, right? So the decision is not that clear-cut. You think this server is too small, then a digression, how fast there will be a new one that is enough? Well, here we have an IBM ASCII-wide supercomputer from 2000 that has 7.2 teraflops. In the second corner, we have NVIDIA Volta graphic card for gamers. It has 7.5 teraflops. This is 17 years of progress. And what's more, the supercomputer weighs in 100 tons. The graphic card weighs in half a kilogram and uses 300 watts, while the supercomputer uses 3 megawatts. So that's the improvement that came in 17 years. So I'm sure if we have a system that's too slow, you can buy more servers. Next year, you can buy more servers even cheaper. So if companies work like this, they need a little different skill set of developers. It's not that they need Scala instead of Java or Kotlin or something like this. They need people who are thinking in a different terms when developing software. So you might have heard about the 10x developer. It's the idea that if you have junior developer and senior developer who knows all the tools, knows everything, he can be 10 times as effective. He can produce 10 times more bugs than the junior developer, right? So I want to introduce you to a concept. It's not new, it's not my concept, but I think it's used here. It's 0.1x developer. So this is a completely different mindset that is not centered on code, but on client value. So such a developer would ask different questions like, let's not add this feature maybe now, okay? Can we just not add it? Or maybe can we fake it so that no one noticed that we didn't implement it? Maybe can we remove some unused feature? I hope you're measuring usage of features in your product so that you know that maybe some of them can be removed. Maybe let's not adopt this new technology. Service mesh, anyone? Maybe let's not automate this, or maybe not extract this class into your company commons utils, right? Let's not optimize it yet. Here are some links if you want to dig deeper. But what happens with all this approach? Well, there's a tweet from I found on the internet. In this picture, you have a browser, 2 tabs. One tab is Gmail. Second tab runs a virtual machine written in Java. This machine in JavaScript. This virtual machine runs Windows 2000, and Windows 2000 runs Internet Explorer. Guess which tab uses more resources? Well, Gmail. So there's something wrong with this picture, right? So it's like Philip K. Dick's Man in the High Castle, right? We see the reality around us. This is the reality, hard reality that is, but there's something wrong with it, right? Because we would still like to go and write this code, write those new services instead of removing them or using some third-party software. So my team thought the same, and we went on a trip to try to discover actually when we can invest in optimization and invest actually engineering time to make things better. So we started with a very large databases conference. It was in Munich, so it was fun. And I really enjoyed the conference. I think this is something you could go there. The conference is about database, obviously, but there most papers that you can see in the internet were published there. There are vendors from databases, but also people like from Intel, NVIDIA, AMD, SAP, Oracle. They show how their databases work, how the software works. The things that NVIDIA was saying there 2 years ago, they are only now appearing in their hardware. So this is a really interesting thing. By the way, how many of you read something like the daily morning paper, at least once a year? Okay, so there will be few papers showing you that it's actually worth it. So if you want to sleep through my talk, no problem. But if you want to take one thing out of this, please read papers, especially those from 70s or 80s. They're the best. So. At this conference, there was a keynote. As all good keynotes, it was fun and informative. And it went something like this. Let's take a biggest commercial data store by any company might have, apart from maybe Google, Facebook, Large Hadron Collider. You can buy a database that will answer any query on this data. Maybe in 2015, in 150 milliseconds, then 80, then 20. The human perception is about 200 milliseconds. So their conclusion at this conference was that the database is solved problems. There's no point in actually what are we doing here? Why are we developing anything? There's no point here. So that's not what we were looking. But if you think about buying databases, that's what they thought at that point, 2 years ago. Fortunately, we started reading papers from 90s, from 80s. There were very interesting things about how to optimize stuff, and few were very notable. Let me show you one, efficiently compiling efficient query plans on modern hardware. If you look at those papers, most of them say doing something on modern hardware, but it was in 90s, so probably it was 2-core server. But what the authors here did, they took some industry standard benchmark, which is some data set, some queries, and the vendors would take this data set queries, run it on their database, and report numbers. Okay, we are faster. We're faster than Oracle. We're faster than MySQL because this benchmark says that. So they took this benchmark, ran one query on DBMS X. If you see this in a paper, probably it's Oracle. 28 seconds. That's how long it took. Then on MySQL 4, at that point, it was 27 seconds. MongoDB was a cutting-edge columnar analytical data store at that time. It took 3.7 seconds. The last thing they did is they coded a C program that ran those queries. It didn't parse the query, or it wasn't a database. It just implemented the logic of the query. This was probably a first microservice. It was 220 milliseconds. So they showed that actually you can buy off-the-shelf stuff, but you have a database running on customized hardware costing millions that is 100 times slower than a code you can hand code each C. So at that time, this was very influential paper. And this was a first hint that actually we're going to right direction in terms of looking for the reason to optimize stuff and how to do it. The second paper is the best trolling I have ever seen. The scalability, but at what cost? The idea here, Mr. Frank McSherry was the main author who then wrote many blog posts about follow-ups to this paper. What they did is they took some data set from Twitter. It was social media graph from Twitter. And they said, OK, there are several papers, several commercial or non-commercial systems saying, OK, we run on 16 servers or 128 servers. When you give us this data, we'll give you the result in 2,000 seconds. And this is state of the art. So there's one publication that on Spark, you run this Twitter dataset, and in almost 2,000 seconds, you get the result. There were other state-of-the-art systems running on 16 on 128 cores. This course is summary of all the cores, but these were distributed systems, so it was on many servers. And they said, okay, but we are now going to introduce some new candidates for the state-of-the-art, and these were by writing some for loops on my laptop. So after reading this paper, I will never look the same at all the clusters of Sparks, Flinks, and other stuff run at the other companies. You might go to people maintaining this system and ask them if they try to run this job that runs on 128 servers on their laptop. Because the result was that 153 seconds. On one core, on a laptop. So the idea was here that there were some inefficiencies built into all those systems. It's not their fault sometimes that it's so slow. It's because it's distributed or there are some other things. By the way, the data set was 3 gigabytes. So this means that actually, how it happens that they actually saw those results and said, there's something wrong with them. We can do better, and we can do much better. It's 128 times faster, sometimes 500 times faster. And what's interesting, the cost in the name of the paper, it's the configuration that outperforms single thread. So you have this cluster of Sparks, and the cost of it is like 100. Means that 100 servers you need to put 100 servers to be faster than your single thread on a laptop. What's interesting, there were some platforms that had infinite cost. So no configuration ever would be faster. But obviously, like Xcad says, Houston, we have a problem. Well, that's a negative. No, there are no problems, only opportunities. So this is opportunity for us, actually, to try to optimize something if we know that we can achieve increase in 100, 1,000 times faster. There will be, I guess, no one will try to say that it doesn't matter and it doesn't bring value to the customer. So instead of 0.1 X developer, we can have 10 times developer. So, but how can we be like those people? How can we be those 10 times developers in the sense in these papers? Well, they definitely had some intuition about what is possible on hardware, because if you see 3 gigabyte data set crunched by 120 cores in 2,000 seconds, there's something wrong, because you know that how much memory you have, how fast it is, how long does it take to read it from SSD and stuff. And I will show you these things that can impact on the hardware level, impact these numbers, and how we can achieve such improvements. All this will be in Java code. There will be small snippets of Java code. On my GitHub is the full repo. It's Java because it's not abstract. If I tell you about some hardware things, it's not abstract, and you don't need to write assembly or C to actually benefit from this, because all the examples will be in Java. This means that all our Java code can do this. First, some refresher of how the servers look like. This is an example of a 2-socket server. There's a lot of moving things here. So I have only 20 minutes, so we will look only at memory. We have cores. Cores communicate with caches. So we have L1, L2 cache. Usually it's core local. So the core has this cache just to itself, and it's inclusive. So if something is in L1, it's also in L2. The L3 cache, it's shared, and it's a victim cache. Victim means that if you load something here, and it means that you need to throw away something that was previously there, it will go to L3 cache. So the idea is that you will probably need that soon, so it will be still close to you. There are memory controllers that connect to RAM. And what's interesting here is that this is a two-socket server. It looks like something like this, two sockets. And the RAM banks are connected to individual processors. When we program, when we create variables in any language, we don't specify which where this variable should be. We have a unified view of those memory banks, but it's not true. They are not equal. So in order to communicate and fetch data for this core from here, they need a link between the processors. It's called on this graph QPI, Quick Path Interface. Intel has improved it, and Intel marketing decided that quick path is not quick enough, so right now it's ultra path. It's obviously faster. AMD had something called hypertransport. Right now, it's called Infinity Fabric. So if there's something like too much Marvel, then you have it. But obviously, it's faster than hypertransport, right? So this communication goes here. And because this RAM are in different locations, this is something that's called NUMA domain. NUMA, which means non-uniform memory access. So if you're in here, and your program tries to access memory, access here will obviously be faster than access here. But does it even matter? Well, it depends on processor architecture. You can have something like this. This is AMD Epic part from first or second generation. So it's Zen or Zen Plus. These are cores. CCX is a core complex. It's about 4 cores here. And you see that there are 4 controllers here, so there are 4 NUMA domains. And if we are working here, our thread is here, and it wants to access memory that's here, then obviously we have, well, it depends how you read this, but there may be up to 3 hops to get to that memory. This is how this processor, AMD processor, looks like if we try to visualize the topology. This is the command to use it. Fortunately, Amazon bought a lot of AMD processors, so it's easy to compare because you can just buy the servers on Amazon from Intel, from AMD. So let's try an experiment and see if this location and collocation does matter. The experiment is like this. When we have even loop systems, when like NETI, when there are threads that are handing over tasks between them, this is something that will impact them. So because one thread needs to hand off work to the other and needs to put some data somewhere and signal the other thread that it's already there. So our experiment will be like this. In core 0, we will have one thread. We'll pin this thread there. So actually it will run, we make sure it runs there. There's some RAM that is the closest to this core, and we'll put the variable there. We'll use it something like atomic variable using unsafe. And in our experiment, we run threads on different cores and measure how long does it take for those two to communicate, in the sense that core 0 will try to flip this variable from 0 to 1, and the other core, when it sees the change, it will try to flip the variable from 1 to 0. This is the libraries I use. I use JMH and JNUMA. JNUMA is the library that will allow me to control where all this stuff is placed. Do you guys know JMH? Oh, okay. Are you sleeping? That's fine too. Java Micro Benchmark Harness. You might consider it something like JUnit for benchmarks. So there is a setup method and a benchmark method, and it was designed by Alexei Shipilev to actually make sure that the code you benchmark is isolated and it's not gets optimized away by JVM. So like the common problem would be if you run a for loop in main, then JVM would say, okay, this code does nothing, I will just remove it. So your benchmark will take 0 milliseconds. And there's a lot of other stuff that's built in to make benchmarking better. But this is micro benchmark, so you can benchmark how fast it is to like put variable into memory, flip a bit, or something like this. It's or on a little bigger stuff, but it's still micro benchmarks. This is some code that will swap this. So we have one thread swapping flag from 0 to 1, the other from 1 to 0. And this graph shows how long it takes. If we put both threads in the same NUMA domain, then it will take 220 nanoseconds. So we can see here if it's the same NUMA domain. If we're just unlucky, because we run JVM or GC moved everything somewhere else, and the Linux kernel moved the threads, and one thread is here, and the second thread is, for example, here, it takes 500 nanoseconds. And then it moves again, and it will take, for example, 650 nanoseconds. So it's still fast, but it's only for one operation. You're losing 3 times the speed just by this locating it in a different place. This is the same graph, but it just shows it in a different way, so we might skip it. Intel has simpler architecture because there's there aren't so many connections, so it was more consistent. We can see that here is one time, and this is the second one. So there are only 2 domains, not 6. Okay, there's another test is the read throughput. So we know that the latency will suffer if it's placed in a wrong memory bank. But how about just reading this data? So we have terabytes of data in RAM, and just we want to just go through the RAM, scanning it and doing some operation on it. So this is a simple test when we just pin the thread to some node and then go through byte buffer in 8 byte stride, reading longs. The simplest thing you can do in Java, you're just reading longs throughout the memory and accumulating result. Then we return the result, and JMH makes sure that this is not optimized away. And it invokes this many times, so actually you can be quite certain about the results and the repeatability of the result. This is the result. For AMD server that I tested on, it's almost 18 gigabytes per second. Think about this when you access some slow invoicing software or slow web page, that actually one thread can read 18 gigabytes of data out of the RAM. And we can see here, I tested this on a three NUMA domain server, and it doesn't matter how far it is. There's prefetcher, there are other mechanisms that work for us. So actually, on big server, you can get more than 100 gigabytes of aggregated memory bandwidth from for our calls. There are tools from Intel, for example, that can run this test for you and show you the numbers. So what this server is doing, if I go to Tauron webpage and I want 12 invoices, so it probably runs on iPhone, right? From first generation, if I wait 1 minute for this. What are these numbers here? It's I changed the benchmark a little, and I made the accesses random. So instead of going through the memory in a linear fashion, it went to the same amount of memory, but randomly. And look, it's 400 megabytes instead of 18 gigabytes. So there are techniques to change, if you can change the algorithm, that can change a random access into linear access, and you can get how much, 10 times, you can get 20, 30, 40 times improvement just in this. And here the NUMA domains matters, because prefetcher will not help you if the stuff is far away from your core. You're paying even more for this. Okay, so why, if you write a program and you have some algorithm, why it doesn't run at 80 gigabytes per second? Because obviously there are other things that happen in a processor, in a JVM virtual machine. And let's assume a case. We have 100 million clients who bought something from your website or your app. We have a column in the database that says how many things they bought. It's integer, so it's 100 million clients, integer, so it's 400 gigabytes. And let's think, how fast can we go through this 400 megabytes and check how many people bought more than maybe 10 units of something, if these are just numbers. So based on this, it's a linear access. If we have 18 gigabytes per second, so probably we should go, like, it should take about 12 milliseconds to go through all this data, right? Do you think that this is how it will turn out? There's a quiz, but I guess it depends is the right answer, because we have just 8 minutes. So just let's go to the answer. This is how the code looks like. We still go through the buffer that we know is 400 gigabytes, 400 megabytes. It's 100 million integers, and we evaluate the predicate. So we want to count here how many people bought less than this number. So, how fast can it be? This is the result. And it depends, obviously, on the branch predictor. Because if we go through this memory and evaluate the predicate, if no one bought anything and the predicate always matches or always fails, it is 43 milliseconds for this case on this server. But if some people bought something from our service and the predicate sometimes matches, sometimes fails, the branch predictor cannot predict what will happen next, and we will mispredict every time. So we get 533 milliseconds. So depending on whether our conditionals are predictable or not, we can get about 10 times penalty for not being predictable here. The question is, can we do something about it? There's a lot of techniques that can be used. One of those techniques was described in the 70s by no one other but Leslie Lamport, and the person known for Paxos algorithm, right? So he said, if you will not get into this, but if you get a set of binary operations, okay, you have, for example, a predicate saying 42. Count how many records match 42 or are lower than or greater than. If you apply several operations like masking, XOR, and to the incoming values and this 42, in the end, you will get 1 here if it matches and 0 if it doesn't match. So we can replace this if with some set of instructions that will return 1 if it matches and 0 if it doesn't match. Here, it's very convenient because we want to count this, so we just add this one to result, right? So instead of the if, we get something like this. We get value from the buffer, we do AND, we do XOR, we do AND, we do mask, we add, we replace it with a lot of instructions, right? So how fast it can be. Oh, and we do bit count. So it's a lot of instructions instead of simple if. It's 97 milliseconds. It means it's slower than the best case, but if the branch predictor misses only 5% of times, this technique is already faster. And what's great about this technique is that if you know your value will match, the highest value will fit in, for example, byte or short, and you have a largest register of long, then you can put many such values in a long, apply all those arithmetic operations, and you will get vectorized processing for free, even without vector registers, because these operations will not interfere with each other, and you can pack those values into one register. And I did it in the code. You can look it up on GitHub. It's even 11 milliseconds. So this is theoretical limit, and here we are running at the speed of memory. It doesn't matter if there's no branch predictor here. The whole logic, the database, you can write this way a database, and I guess it will be faster than many. Obviously, this technique is not always great. There's a DOM on GitHub that was compiled by a compiler that does not use branches. It uses only MOV instructions. The problem is that it renders one frame every 7 hours. So it is not always the best and only way to go. So summing up, there's two kinds of developers skill set that one might have. 0.1x, 10 times developer. These two hats are not exclusive. You can wear both of them, depending on the situation. If we want to go and optimize, this is something what is required. Obviously, if you need to, because you might be working on IBM, and you can spend years on optimizing stuff, and then the project goes to the trash can, and no one cares, right? But most companies doesn't want to spend all those money, so you should please read papers, experiment, develop the intuition of what is possible on current hardware, on future hardware, on hardware you're using, and that's it. So the answer is it depends, but with proper tools, we should know better and be able to decide. Thanks.